Then he's been worked in many, many places on the globe. But in 1998, he went to Grenoble, and I just saw, became a professor, classe exceptionnelle. So that sounds good in French. Something exceptional professor. He is an emeritus now, but that doesn't, he's still active. He's a petrologist and geochemist, very wide interest. And I just put on including habitat of life on the early Earth. Nick is a member of Academia Europaea, elected fellow Geochemical Society, is very well cited. I think there's more than 30,000. For those who are aware of H indexes, a colleague of mine, Carmen Gainer, told me if you have an H index which is more than your age, that's very exceptional. And Arndt has 91, and that's well above his age still. Today, and since he's changed the title from one I had, he will talk about when and how did continental crust form. So the floor is yours, Nick.
So thank you very much, Trond, for the introduction and for inviting me here to Oslo. I came on Monday afternoon, and since then I've been having a wonderful time talking to Ryder, to a lot of different people in the center about all sorts of things, magma oceans, Indian crust, passage of granite through the crust, and so on. Had a good time, and I think this will continue. Today I'm going to talk about formation of the continental crust and what this tells us about how the Earth operated 3 billion, 4 billion years ago. Now, after I retired, I spent 4 years in a small company, and it was called the vie active in French, which is in the active life. They call it, if you work with industry, this is active life. This finished, and now I've gone back to the passive life in academia. I restarted research. And when I started reading again, I came across, this statement. There is a broad consensus that Archean granitoids formed by partial melting of hydrated mafic rocks in a stagnant lid geodynamic regime. And I said, that's not right. That can't be right. I didn't like the idea. I don't think it's right. So this is what I'm going to try and convince you of, that it's not, there was not a stagnant, immobile lid covering the whole globe through most of the Archean. I'm going to ask questions like these. When did plate tectonics start? Was there a major change in the geodynamic regime sometime through the Archean, indicating that earlier on there was another geodynamic regime? Related to this, but not entirely the same question, is when did subduction start? And we can talk about the difference between subduction and plate tectonics and whether they are one and the same or can be separated. And to address these questions, I'm going to consider how was granitic material extracted from the mantle to form the continental crust? Because I think if we understand this process, we can get a better idea of the geodynamic regime that operated through the Archean. So if you look at the literature, you find a lot of diagrams like this one here. Many geoscientists support this idea of the general consensus, that Archean geodynamics was very different from modern geodynamics. And they talk about a stagnant lid, an immobile lid that covered most of the globe, under which the mantle convected, perhaps with mantle plumes and so on. And there was a transition at some time, here they put it at 1 million years, between this stagnant lid regime and a plate tectonics regime. And you find a lot of terms in the literature like this. A stagnant lid, they talk about drip tectonics, they talk about sagduction rather than subduction. The heat pipes is another thing. And the question, was there no plate tectonics in the early Archean? Now, why do so many geoscientists believe that there was no plate tectonics? Now, there are various approaches to this question. One is shown here. This is Bob Stern, who said, what are the criteria of modern plate tectonics? And he identified a number of geological features: kimberlites, ophiolites, blue schists, ultra-high temperature metamorphism, features that we associate with modern subduction zones. And he found that these features, we don't really see these features in rocks much older than 600 million years through the Paleozoic, but not before. He argues then that plate tectonics started only somewhere around there. I don't think this is the case, mainly because there's no reason to believe that subduction, if it operated in the Archean, would be just the same as today. The conditions were different, and subduction probably was different, and you don't retain these features. Another line of argument for saying there was perhaps no plate tectonics in the Archean comes from comparison with other planets. Stephanie knows about this. The idea shown here is that today, contemporary Venus does seem to have a stagnant, immobile lid, mafic material. We're not sure of the composition, but there seems to be a lid. It didn't move. There were not rigid plates that moved across the planet, which is the situation on the Earth. So the idea is that at the start, Venus and Earth were similar, but they evolved in different ways. The Earth to plate tectonics, Venus staying with this stagnant lid situation. And there are a large number of other changes which seem to have happened around here between 3 billion years and 2.5 billion years, which are also said to indicate a change in geodynamic regime. For example, this is Shari and Richardson, who noticed that eclogite inclusions in diamonds are present after 3 billion years, not before. These eclogite inclusions are interpreted as subducted oceanic crust, which are caught up eventually in the diamond. The fact there are none that we know of older than 3 billion years was interpreted by Shari and Richardson to say no plate tectonics beforehand. There are also a large number of changes in various geochemical ratios. There's some sort of break here at 2.5. For example, the potassium content of granites became much, the potassium content, this sodium-potassium ratio, potassic granites only start to appear in large amounts after about 2.5. There are breaks in geochemical ratios which can be documented, and they are interpreted to say there was no plate tectonics beforehand, no subduction beforehand, subduction and plate tectonics afterwards. Then there are the geochemical models, shown as, for example, calculated on the basis of isotopic data. And I'll just point this one here from Bruno Duim and his group. They calculated this shows the rate of growth of continental crust to its present volume here from something 0 at a 4.5, relatively rapid growth with a kink here, which they interpreted as the onset of recycling of continental crust, which they equated with subduction. So they distinguish between what they call a pre-subduction regime from a regime in which there was subduction. So the various lines of evidence, looking at geological features, looking at models, which support the idea that there was no little plate tectonics before, about 3 billion years, and that plate tectonics started after that. But perhaps the most compelling argument for a different geodynamic regime in the early Archean comes from estimations of the temperature in the mantle. There are a number of theoretical lines of argument which would say because of higher radioactive heat production, because of heat loss from the core, heat loss from accretion, temperatures in the Archean mantle were significantly higher than those in the modern mantle. This is a diagram from Claude Hertzberg, age, and the potential temperature, which is the temperature of the sources of various types of basalts. We just concentrate on the black squares, which are called non-arc basalts. They're basalts which are interpreted to come from the mantle directly. He has a way of calculating the temperature, and he showed in this diagram that temperatures of the sources of these basalts were maybe 250 degrees higher than those in present-day mid-ocean ridge basalt. So Archean mantle may have been much hotter. And why is this important? For two reasons. First, I show in this diagram, this is temperature, pressure, depth for mantle peridotite, the solidus, the liquidus, the start of melting, the end of melting, and I show two ascent paths. One is the ascent path of modern mantle material rising up beneath a mid-ocean ridge. It hits the solidus at relatively shallow depths and undergoes melting paths to arrive at the surface with about 15% partial melt. Compare this with the ascent path of hot Archean mantle, which hits the solidus much deeper, undergoes a longer melt path, and arrives at the surface with 40% partial melting. So a large volume of magma is produced here, a small volume here. If this magma arrives directly at the surface at a mid-ocean ridge, it'll form oceanic crust. The cool modern mantle, short melting path, small volume of melt produces thin oceanic crust. The hot Archean mantle, large volume of melt produces thick oceanic crust, maybe 30 kilometers thick. So that's the idea. Most probably through most of the Archean, the oceanic crust was much thicker. It's composed of plagioclase, which is a low-density mineral. So we have a thick, buoyant crust which probably resisted subduction. This type of thinking then leads into models of the type I show on the top here. Numerical modeling conducted by the group from Jeroen van Hoenen in Durham. He runs numerical models of mantle convection. And what we see here are a series of panels with different delta T. That's the temperature difference between the modern mantle and a mantle that is 300 degrees hotter. We see that for a modern mantle, he's able to produce something that looks like subduction. Crust is being subducted and it's going down to the base of the goes down deep, perhaps to the transition zone. As the temperature increases, subduction becomes less obvious and it becomes discontinuous. It doesn't penetrate deep. So according to this sort of model, it is said that subduction was difficult or impossible through the Archean. This then leads to alternative models for the geodynamic regime within the Archean. For example, here's from the Terrascaia group in Zurich, and they start with quite a different situation. They start with what's called the stagnant lid model, as for Venus. They assume that there was a thick layer of basaltic crust at the surface, which converts to eclogite at high temperatures at the base of this crust. Now, eclogite is the high-pressure equivalent of basalt. It is dense. So this dense eclogite drags down the lower part of the crust into the mantle. They talk about eclogite drips, and partially melts to produce. This is the sort of stagnant lid regime that they consider to operate through the Archean. So here we see it, the contrast between, on the left, according to these authors, a stagnant lid regime with sagduction, dripping of stuff from the base of the crust down into the mantle, as opposed to plate tectonics and subduction, and the same sort of transition is shown here. Now, how do we distinguish between these two situations? Plate tectonics, in which rigid plates move down into the mantle and act in that way, from the alternative idea that there's a stagnant lid, the base of which drips down to the mantle. I'm going to focus on formation of the continental crust. formation of the continental crust, which essentially is a process whereby material of felsic composition is extracted from the mantle and finds its way to the surface. And I'm going to ask the question, when did the continents start to grow and by what mechanism? To try to distinguish between these two alternatives, stagnant lid versus plate tectonics. So we need to now consider continental growth models. At what rate did the continental crust start to form? Do we see evidence of continental crust forming early? I'll talk first about the rate of continental crust forming, and then talk about how it could have formed. But first, when did it form? And we see there are in this diagram here, time versus the fraction of continental crust. I showed you one curve like this. It showed rapid growth of the continental crust early and then late, so on, later thereafter. There are some models which talk about rapid continental crust either in the early Archean or the late Archean, and another set of models in which there was very rapid formation of continental crust early in Earth history. Richard Armstrong developed this idea in the 1980s. He said, right early on in the Hadean, continental crust was extracted from the mantle and continued to accumulate thereafter. This idea has been taken up by the group of people working with Jun Koranaga, two papers here. One model they have this is showing the accumulated volume of continental crust, and this is the rate of continental crust. But in both cases, continental crust grew rapidly early on, and thereafter, the volume of crust remains pretty constant because growth is counteracted by recycling back into the mantle. I don't accept these ideas because of information that comes from zircons. You may know that first in Australia, and now almost everywhere, many other places, including India, people have found zircons with ages that correspond to the Hadean, with ages over 4 billion years. So here, what we see in this diagram, age, and these are the determined age of these zircons, the only minerals we get from the Hadean, we see from the Hadean. Showing also in this diagram are the hafnium isotopic compositions represented as hafnium. Now, the way we interpret this diagram is to say material in the mantle will evolve along a curve like this. It is depleted, and because of that, the epsilon hafnium ratio increases. Material from old continental crust will evolve along a line something like this. Here we see the compositions of the zircons which lay between these two curves with very few, almost no data coming from here, all the way up to about 3.8 billion years. Then suddenly we start to see these zircons with compositions like those coming from the mantle. For me, this is very significant because this general trend of decreasing epsilon hafnium with age corresponds to repeated melting of granitic material, felsic material. So it seems that felsic material formed here and material of the same composition melted repeatedly in a closed system with no input from the mantle. Input from the mantle started only here. So I interpret this to indicate time of persistence of a stagnant lid, enriched mafic material which was at the surface, which melted repeatedly until this stage when there was a change in the geodynamic regime. From here on, in my interpretation, this is when subduction, plate tectonics started somewhere around here. So this is a Jack Hill zircon, 4 billion years, an image of a zircon. This is the model proposed by Tony Kemp and co-workers. They envisage a stagnant lid composed of basalt. It's very hot because It had a high concentration of radioactive heat-producing elements. It melted internally to produce the granitic melts from which the zircons crystallized. So early on, there was a stagnant lid, some sort of stagnant lid, which disappeared around 3.8 billion years. So I think we can eliminate this first idea, early Hadean subduction. There was something different then. But how do we distinguish between these two other alternatives? The idea that around 3 billion years, we saw a transition from what they call pre-subduction to a early subduction regime. How do we distinguish between those two alternatives? And now I'll focus on granitoids. How did the granitoids form? Because before we talked about the rate of growth of continental crust, I think there was not much until about 3.8, and from then on the continental crust started to form. But how did it form? What sort of geodynamic regime in the early Archean formed granitoids? So we can contrast the two alternatives, subduction, plate tectonics, subduction, melting in a mantle wedge and so on, which happens now, with the pre-plate tectonic drip tectonics regime, in which you have a thick layer rather like that which I envisage for the Hadean, but a situation in which the lower portion of the mafic layer destabilizes, drips down the mantle, and partially melts to form felsic magmas, which form the continental crust. In other words, granite formation in a stagnant lid regime. Perhaps the main advocate for this type of model is Jean Bédard in Ontario, who produced this diagram. He uses the term sagduction, which is a process in which the base of an oceanic plateau or a thick oceanic crust consists of basalt. This basalt converts with high pressure to dense eclogite. It sinks into the mantle, heats up, and triggers the formation of granite. Is this a viable process? This is what I'll talk about now. For example, here, another paper from Carwood et al., showing a thick mafic pile, a thick pile of mafic material, almost 30 kilometers thick, in which granitic magmas form by melting at the base of this crust, which produce magmas that rise up into the upper crust and gradually convert the crust into felsic material, felsic continental material. Now, to evaluate this, I give you my recipe for granite, which is very simple. You start with basaltic material. You need water. This is essential. You need heat. And mix the two and you get a granite. But I emphasize this, you need both. You need basaltic material, which can be either solid basalt, which heats up and partially melts, or it can be hydrous magma. Both work, and I think probably hydrous magma is more important. You need water, you need mafic material. If you add heat, you can get granite. But what situations can this occur? My spelling corrector doesn't know the term mafic, and it keeps on saying I really need to be talking about magic. And I think he or she is right, because thick oceanic crust doesn't look like this. You need magic oceanic crust if you want to produce granite within it. Sagduction and in situ crustal melting models don't work for two main reasons. First is thick piles of basalt don't really exist in nature. If a large amount of basaltic material is extracted from the mantle, it doesn't accumulate as a thick pile with uniform basaltic composition from top to base. It differentiates, and I'll tell you what differentiate means. And second, the lower portions of a thick pile of basalt are not hydrous. There's no water there. So I think these are important messages, and I'll explain why I think this is the case. First of all, we have many examples at different scales of piles of material with basaltic ultramafic compositions. From one a 1 meter thick komatiite flow in which the lower portion is olivine cumulate, the upper portion is liquid. This is the Bushveld complex, 9 kilometers thick with the basaltic material at the top, the lower part which has ultramafic composition, ultramafic cumulates. And this is the Ontong Java plateau, in which the basalts at the surface are normal basalts, but the seismic data shows high seismic velocities, which are best interpreted as ultramafic cumulates. There are sound petrological reasons for saying that thick piles of mafic, ultramafic material do not have this constant composition throughout. They're differentiated. One argument is that if you look at the composition of basalts that erupt at Ontong Java or in Archean greenstone belts, they have low MgO contents. But we know from experimental petrology that if you melt the mantle at 60 kilometers, 100 kilometers depth, the composition of the melt that is produced is much more magnesian. So a primary melt from the mantle has 15 to 20% MgO. The basalt at the surface has 5 to 7% MgO. You go from here to here by fractional crystallization and the accumulation of a lot of orthopyroxene, of a lot of olivine plus orthopyroxene. The second argument is we know systematically in all contexts, whether it's an island arc, accreted margin, whatever, only a fraction of the material gets to the surface. Only a fraction of the magma from the mantle gets to the surface, and a large proportion, 50, 80%, is intruded into the crust. So if we take into account that the primary pickrite, which is dense, will accumulate here, this adds to the idea, the accumulation, the differentiation. The mantle is different. The thick pile is differentiated. Basalt at the top, ultramafic, infertile cumulates at the base. So, can melting within thick mafic crust produce voluminous granitic magmas? I say no, and I'll just go back. And also, the water is here. The water in crust comes from interaction with the seawater, but it's at the surface, it's not the base. Melting within thick crust cannot produce voluminous granitoids because the fertile plagioclase-bearing material, which is said to convert to eclogite to drag the material down the mantle, doesn't exist, is absent in the lower part of the crust, and water is confined to shallow levels. So that's the situation. If you have a layer of crust, the lowermost material is at the base and it's dry. But there's a possibility that perhaps the lower crust is denser than the mantle. Perhaps it's more iron-rich. And if you have a dense layer of iron-rich cumulates, this might destabilize and form a diapir, which will drag material from the crust down to the mantle where it might melt. So we looked at this. This is Alberto Romain was a postdoc in Paris, and he was working on this. And we asked him to numerically model whether this was possible. If you had a crust that looks like this with a dense lower layer, could destabilization of this lower layer forming a diapir drag into the mantle, deep into the mantle material from the top of the crust? So he did the models. So we have time dimensionless, depth dimensionless. This shows what happens with the lower crust. It goes down into the mantle. Initially, it drags down a little bit of the crust, but then it decouples and the material stays at the surface. As I expected, and I was very glad that his models reinforced my prejudices. He did something else which is also interesting, and this bears on the water content. Could there be water in the base of a thick pile of mafic material? So in the literature, you find the idea, it's called the heat pipe model, the idea that if lava flows erupted one after the other very rapidly, the first lava flow would become hydrated at the top. And then if another one arrived immediately afterwards, it would bury the earlier ones, and so the lowest, here we see a temperature profile, the temperature in the lower ones would remain fairly low if the eruption was rapid enough. So this works. If you had a situation like this, the temperature in the lowermost hydrated lava flows could be relatively low and water could be retained. But if you take into account the fact that a lot of magma is intruded, the magma is intruded, adds heat to the lava, to the pile of mafic material, and the temperatures inevitably go up. So this is the situation as I see it. The stagnant lid model doesn't work because the crust is differentiated, the water is near the surface, the lower part is olivine, pyroxene, cumulates. If some water were to penetrate one way or another deep into this pile, perhaps along fractures or something like that, if this material was dragged down deep into the mantle, what would happen? Dehydration would release water, which would simply move up from hot rock to cold rock, from hot rock to cold rock, and it doesn't cause melting. So in my opinion, any in situ melting process or any sagduction model doesn't work. It cannot produce voluminous granitic magmas. It cannot produce continental crust. On the other hand, contrast this with the process we know well, which is subduction. Subduction, in which the oceanic crust is hydrated partially at the mid-ocean ridge, but dominantly when the slab bends and fractures as it goes down the chute here. Then it undergoes dehydration. Large amounts of water move up into the mantle wedge where they trigger melting to form the parental magmas of continental crust. Nowadays, and I think the same thing happened in the Archean. But what about these arguments I talked about earlier? The argument that the mantle was too hot to allow efficient subduction. This argument here. More recently, other people have looked at this question. This is a more recent paper by Gan and Feng, looking at the same type of rocks which are considered by Claude Hertzberg, applying the same sort of method, and they found numbers like this, potential temperatures which are not much hotter than those of the modern mantle. So this notion that the Archean mantle was significantly hotter than the modern mantle is not necessarily correct. But even if it were correct, I want to go back to this diagram here, the modeling of van Hunen. And there's something important here. He seems to have modeled a nice subduction zone here, but even at the highest temperature, we seem to see oceanic crust being taken down into the mantle. Not very long, not persistently, perhaps not permanently, but in a transient manner, hydrated oceanic crust is taken down maybe 200 kilometers, and that's all you need, because magma production in a modern arc happens in the upper 100 or so kilometers of crust. So this is the way I see it. Subduction may have been shallow, short-lived, transient, but it's the only process that can produce large volumes of granitic material that forms the continental crust. This is not to say there was plate tectonics. I've sort of been waffling a little bit by talking about subduction and plate tectonics. It's not necessarily the same thing. The existence of transient, shallow, impermanent subduction zone does not mean that there was not a largely immobile lid covering the rest of the planet. We could have had some sort of transition zone, but the main point is that to form the continental crust, you must have had subduction. Okay, so preliminary conclusions. Now, I gave this talk a while ago in somewhere else, and when they saw preliminary, there was an audible groan from the audience saying, is there more to come? And I'm afraid there is a bit more to come. But we'll just talk quickly about the main subduction. Sagduction cannot produce voluminous granite. Most continental crust in the Archean now formed in subduction zones. Subduction may have coexisted with a partially immobile lid throughout the Archean. Next. Then Trond, I'm supposed to check the time, about 40 minutes, and indeed it's exactly 40 minutes. Wow. What about these changes, though? What about the changes that seem to have happened around 2.5, 2.8 billion years? John Dewey, he had this nice statement. The time distribution of almost everything shows a rapid change from in the period from 3 to 2 billion years old. What happened then? Does it indicate a change in geodynamic regime from the subduction regime to a pre-subduction regime? I would say no. I would say that these changes are the consequence of several ongoing processes, continuous processes that simply reached some sort of nexus around this time. The changes that are taking place are mantle temperatures, probably evolved along a curve like this, that not to scale. Probably the ocean volume changed. The oceans there's more water at the surface of the Archean Earth than now, simply because as the mantle cools, transport of hydrous material in the plates into the mantle becomes more efficient. So probably now there are probably there's more water in the mantle now than there was then, which means there was less water at the surface. At the same time, the continental crust was growing by subduction, I would maintain, and the land surface was increasing. As the ocean level went down, as the continents grew up, there was more and more emergent land. So these processes can explain most of the changes that we saw. For example, the growth of the continental crust progressively takes more granitic material at the surface, at the site where new crust grows. So if new crust grows in a subduction setting, the magmas from the mantle will assimilate a certain amount of pre-existing felsic material, and this increases the potassium content of the subsequent granite. This assimilation process changes these ratios and explains a lot of the discontinuities we see in the profiles. Decreasing ocean volume, I mentioned that. Emergence of land. Once you have emergence of land, you can get sediment erosion, sedimentation, formation of detrital sediments which go down, fed into the site where the granites form, and this also contributes to the changes in composition. There are others which I grayed out because I don't really want to go into them, because I want to focus on this last process, which I think is interesting. The idea that continental crust did not grow regularly, and instead there were episodes of rapid growth of the continental crust separated by periods with very little growth. The evidence from this comes again from zircons, not the Hadean ones, but the more modern ones. Here's a compilation of the ages, the uranium-lead zircon ages of zircons from various localities. The red curve shows zircons extracted from granites. The green curves show the zircons in large rivers, detrital zircons in rivers. And what we see is there's not a continuous distribution. There are large peaks separated by troughs. 2.7 is the biggest one. 2.5 is a real peak. It's common in India and China, and it's probably just about as big as this one. So how do we interpret these? Again, with geology, there are alternative schools, different interpretations. There's one school which I call the creationists. And the creationists think this is a primary process driven by mantle convection. The idea that the mantle doesn't convect regularly. There are peaks in which mantle convection is accelerated for one reason or another, which leads directly to peaks in the rate of continent growth. And I'll explain why this might be the case. The alternative, the preservationists, point to calculations made at a modern subduction setting where the rate of continental addition, continental growth, is about the same, look at these numbers, about the same as the rate of destruction of continental crust. through subduction of sediments or erosion at the base of the crust. So they maintain that in a normal subduction regime, there's no net growth of the continental crust. They say that continental crust is only retained during continent-continent collision, as during the growth of supercontinents, where zircons are preserved in the interior of the continents. So for them, the peaks represent periods of enhanced preservation of continental crust, not periods of accelerated growth of the continental crust. And their arguments look something like this. In this scandalous diagram in which they've combined the two peaks at 2.5, 2.7 and 0.5 and said this corresponds to the supposed position of a supercontinent, which they call here Canora. Matt, is Matt here? There you are, Matt, this is a diagram for you, in which for some reason, I have to talk to you about this, because for some reason you said that probably the younger peaks do not correspond to the times of supercontinent accretion or destruction, whereas the Archean ones did. Is that right? Okay, well anyway, this is your diagram. The way I interpret it is there's no evidence of an Archean supercontinent. There's no evidence of two supercontinents here. And instead, there's another diagram from Walter Beaker, another time, and these blobs represent the periods of major continental growth, the zircon, uranium-zircon ages, which don't really correspond to any credible time of supercontinent formation, but correspond to the times of large igneous provinces. So I think that's the important association. I'm going to make the case that the peaks in uranium-lead zircon ages represent, in the creationist model, accelerated mantle convection in the form of large mantle plumes. As we see, for example, in the Cretaceous, when Ontong Java, Manihiki, and Hikurangi all erupted at around 120 million years. Coffin and Eldholm did this very nice calculation. They calculated the volume of magma in the plateau. They assumed 10% partial melting and calculated the volume of the source, the amount of material in the mantle which must melt to produce this volume of magma at the surface. And it's enormous. The volume mantle that must be involved in the formation of these plateaus extends down into the lower mantle. The peaks in the Archean were probably much larger than this one. So with Anne Davai, she's from Paris, we developed a model backed up by her analog experiments, which said at these times, 2.7, 2.5 billion years and so on, a large amount of material moved from the lower mantle and the upper mantle, rather like the plumes. This material heated up the upper mantle, causing it to move more rapidly. But more importantly, the movement of material from the lower mantle to the upper mantle required a return flow, which is subduction. So basically our idea is simply that plumes accelerate subduction. The periodic arrival of plumes corresponds to peaks in the rate of continental growth. So I would redraw this curve, simply saying the continental growth curve was probably something like this, with periods of accelerated growth corresponding to the zircon ages. So that's my final conclusion. Subduction and continental crust formation was episodic, particularly during the period 2.7 to 1.8 billion years. Thank you for your attention.
Okay, thank you, Nick, for a very interesting talk. So is there any questions, comments, agreements, disagreements? Yes, yeah. Must be somebody. Radar, of course. Yeah.
Of course.
So I just wonder, this shallow subduction that you favor for generation of the earliest continental crust and granites, would that be then the same as suggested, for instance, by by Tarasgeria and the Y for Venus. I mean, that's kind of a plume-initiated subduction? So
Well, I think it's very different. There's no water at the surface of Venus, so you don't get. Yeah. So even if you.
But I mean, if there was water.
If there was water, and you see the key difference between what they call sagduction and subduction is the inclination. If something moves down vertically, even if it contains water, the water will just move up into cooler rocks and it won't form anything. What subduction works so very well because you have this conveyor belt which transfers water deep into the mantle where it moves upwards into hotter material, and in that situation, you can produce magma.
So, okay, so then you essentially infer a relatively extensive lateral transfer of oceanic lithosphere. That's what you prefer.
Yeah, I think you require oblique transport of hydrated material into the mantle, which is subduction, and that produces granitoid magma, parental magmas.
Any others? There is.
I would like to talk a little bit along the same lines. You mentioned the work of the Durham group, right? And this initial subduction at 200 kilometers. If I remember well, that's actually their initial setup. It's not a result of the model. That's how they set it up, because you need a subduction zone to drive subduction. So that's not really a test by itself.
Well, this comes back to, we don't know what initiates subduction.
Exactly. That's where I'm going to get at. But the idea that you would have these short-lived subductions, actually Venus gives you examples for that. Because you have places where you have evidence of subductions, but you don't have significant large motion that would correspond to a long-lived plate tectonics. So in a way, that provides us evidence that this is a system that can work.
Okay.
Although we don't necessarily understand it.
No, I think I think it's important to distinguish between long-lived subduction situations in which the oceanic crust is taken deep into the mantle and the situation goes along, continues for a significant time, which happens now, and that's plate tectonics, when you have lateral movement of rigid lids and so on. I don't think that probably didn't happen in the Archean, but it's not needed. If you have a lot of transient shallow subduction zones, that's all you need to form the continental crust.
I just wanted to add something to this, that I think one of the biggest questions also between the sagduction and subduction is that whether you can break the crust and the lithosphere on the surface if you can create brittle deformation, because if something is very hot, then it will rather deform like viscously more in a ductile deformation than like brittle. So the question is, did we have the conditions in the early Archean to break at the surface to create a deeping slab?
Yes. Well, this is I try to explain my reasoning. Continental crust is voluminous. To form large amounts of continental crust, you need to transport a lot of water down into the mantle. And I cannot see how this would happen in any of the alternative models. You need this, for one, it doesn't have to go down far, but hydrated material must go down obliquely into the mantle to achieve this. No?
One here. You get a microphone.
Just to ask your observations, I mean, you have seen a lot of Archean greenstones and granite successions. So just to know from you, so many have contributed on the lines of ophiolites from modern plate subductions and stuff like that. Have you seen anything as close to that in the Archean greenstones, like anything which has like sheeted diet?
Anything that looks like ophiolite? No, you don't.
Not really,
You don't. But I don't think this is a problem because, remember I showed the thickness of the crust. Now, probably in the Archean greenstones, the basalts and the greenstone belts, I think they're oceanic plateaus. but they could be the uppermost part of that oceanic crust. You know, an ophiolite is only what? Thickest ophiolites are 6 kilometers thick. So a modern ophiolite can sample right through the crust and down into the tectonite, the lithosphere. But a slice through the uppermost part of a thick Archean oceanic crust will only sample basalt. And that's what you see.
So in your creationist model or perspective, is there some sort of secular variation through the 3.8 billion years of subduction, since you have this very apparently intense period, or is do you see this recurring before and later?
Here, you know, there don't seem to be any prominent peaks up to this first one at 2.7. There's some suggestion of something around here, but I think that's simply oversampling. You know, people like these old Archean greenstone belts in Barberton and so on. This probably is overrepresented. So no, I don't know. I don't really have any reasonable explanation why, in my model, in our model, the mantle should have operated semi-continuously up until this stage, and then suddenly started to produce these pulses, the pulses which generated the peaks in the zircon populations.
Others? There's another one there.
In your recipe for the continental lithosphere formation, so you need like basalt, you need heat and water. How do we know that in the beginning there was not more water than it is now? And what are the constraints for the amount of water we had in the early years?
Two things. You know, these jackal zircons, the old detrital zircons, are remarkable because they exist. We never expected to find anything from the Hadean, but we found them. They're zircons that have trace element compositions which are different from zircons which crystallize from kimberlites and so on. Their trace element composition is that of a zircon that crystallizes from a felsic granitic melt. But also, by looking at the temperatures, by using various geothermometers, we find they crystallize at relatively low temperatures, temperatures that can only be achieved if there was water in the source. So this argument is taken as evidence that there are already oceans at the surface of the Earth way back at 4.4 billion years. So there are oceans, seem to have been oceans then. Then there's this other question is how much of the water, how is water distributed between the surface and the oceans, and what proportion is present in various forms in the mantle. And then this leads to the idea that the volume of the oceans has been shrinking, has been decreasing as the temperature in the mantle decreases, and as water can be transported more efficiently from the surface into the mantle.
Okay, I had billions of questions, but we can do them in the bar later because I got signal now that we have to stop.
Okay.
And thank you all for turning up. It was a good crowd. And thank you again, Nick, for a great lecture. So.
Thank you.